Okay, in this uncertainties explainer, I'm going to try and take you through the three ways of doing uncertainties. Now, at higher, we're dealing with uncertainties in three ways. And the three ways are random uncertainties, scale reading uncertainties, and calibration uncertainties. And when we've got a reasonable grasp of that, we'll move on to graphs. Now, in order to do this and generate some real data, I dropped a pen lid. And as I've got loads of pens, and I often forget to put the lids on them anyway, I could drop a pen lid. And I dropped it from the top of this cabinet behind me, about 1.8 meters. And I dropped it 1, 2, 3, 4, 5, 6, 7, 8 times. And so what I want to do with this is I want to calculate the random uncertainty and then the mean value. And that's how I would express this data. I'm going to get a mean value and I'm going to give it a random uncertainty. So how do I do that? Okay. Eek. Okay, so the random uncertainty is calculated using the minimum value minus the maximum value minus minimum value divided by the number of values. So on this one, the 0.89 is the maximum value, 68, 65, 66, and the 65, 0.65 is the minimum value. So you can see, oh dear, I've made a mistake. Tut tut. And having done the subtraction and division, I end up with, and this is my absolute, this would be given as my absolute random uncertainty. Now, so this is called the absolute uncertainty in the value, my 0.03. Now, if I've calculated that, and let's just assume it's correct, even though I might have taken that wrong value, then we normally express it as one significant figure. So it's very rarely that I say to you, oh no, I can't remember I was saying just do it to one significant figure. But this is given to one significant figure. And having done that, I will then go on and do the mean. So I've added up my numbers without spotting, and I've got my mean value. So I can now say the mean time for the pen lid to fall was 0.74. So I've rounded this up to two significant figures, and I've got this, and I've got that, as one significant figure. Now you can see, if looking at this value, if I think it's going to take 0.74 seconds plus or minus 0.03 seconds to fall, there's not much point me giving this next decimal place of saying, oh, I should do this as 735, because I actually don't know, within the uncertainty here, forgive me, there we go, within the uncertainty, so here's my random uncertainty, and this is called the absolute value. The absolute random uncertainty. There's no point me, if I don't know realistically whether this is 0.7, this could be between 0.71 and 0.77, because it could be plus or minus 0.03 on this value. So if my true value for how long it should take the pen to fall is somewhere in this range between, then there's not much point me giving it to three significant figures, because I don't know if it's 0.72 or 0.75. I certainly don't know that it's 0.735. So I really cannot use another I really cannot come up with, there should be nothing there. I can't put a value in here because my uncertainty is in this column, and so there's no point having anything built further down. Okay, now one thing that I haven't done is mention that I could give this as a percentage uncertainty. If someone wants to say what's the percentage uncertainty in the time, I would just take the uncertainty. So for the percentage uncertainty, I would just take my uncertainty, 0.03, and divide it by the value, 0.74, and times it by 100 to get that fraction as a percentage. So I could have a percentage uncertainty value, and that's how I would do it. And that's about 4%, he guessed. Now, doing that in my head, I'm thinking that's about 4%. You'll say to me, oh, you're terrible at doing maths in your head. Okay. So, what's next? Answer, scale reading uncertainty. So if that's random uncertainty, scale reading uncertainty. So I decided my task for this that I would set myself would be to measure the length of a Bic pen. Now, measuring the length of the pen in millimeters, I measured it to be 14.4, and I thought to myself, realistically, using this method, the issue here is the actual scale. So whenever you've got an instrument with a scale, you're trying to start exactly at 0 on the scale, and you're trying to come up with some method that's going to get you a perfect start at 0 on the scale. So, and then to read the other end of the scale. Anyway, so I'm definitely not confident that I'm within I think plus or minus 1 millimeter is a realistic value of the scale reading uncertainty with this ruler in this particular setup, especially as the point won't sit nicely against the scale. So if I was measuring the length of this other ruler and it would sit nicely against the end of the scale, I'd feel happier. But it's a bit awkward, this bit biro, and so that's the best I can do, plus or minus 1 millimeter. So I'm confident the pen is more than 143 millimeters long and less than 145 millimeters long. And the true value of the length of this pen lies somewhere within that range. So I express it as 144 millimeter plus or minus 1 millimeter. And this is this uncertainty that we've got here is the scale reading uncertainty. And this is an absolute value. I'm not giving you a percentage. Now, clearly, if you wanted a percentage uncertainty here, you would just calculate that as a fraction of that and times by 100. So you do 1 over 144 times by 100, and you probably get something like 0.65% or something like that. 0.60. So it's less than 1%. So that's my scale reading uncertainty in this case. And just to illustrate to you this, I've drawn a number line in millimeters of the length of this, and I'm suggesting to you that every time I measure it, I could get a different value within this range, but I know that the true length of this pen lies within the range 143 millimeters to 145 millimeters, but exactly where it is, I'm not sure. And I've expressed my uncertainty in that way. Okay, now, we did an experiment. If you remember, this was the one where a certain young lady was not present in class and was active on the computer working with a certain young man. And so and what I've done here is looked at this experiment. If you just measure this angle, say 10 degrees, and say, okay, I know that this is the classic experiment where you have a laser, it shines light into diffraction grating, and the diffraction grate, and we've got our central maximum and our first normal. If you want to find out wavelength, if you put in the numbers for the first normal and say, okay, if you're using a protractor, your scale reading uncertainty, I would have thought, would be at least plus or minus half a degree. So this is just another example of a scale reading uncertainty. So if that's plus or minus half a degree, and I measure 10 degrees plus or minus a half, that's a whole, if I take the uncertainty and divide it by the value times by 100, this gives me a percentage uncertainty of 5%, which is very big, clearly not good in an experiment. And that is why I would always encourage you to design an experiment like this, where you measure a very big angle and say, okay, I'm going to use this angle, and call it double the angle for the n equals 2 line. And then when I use this angle, I know that measuring 50 degrees with the same protractor, my uncertainty is 1%. So that's why it was to reduce this scale reading uncertainty that I pestered you to measure big angles when we did this in class and not measure small angles. Now, to finish off, I want to talk to you a little bit about calibration uncertainties. Because when you buy an instrument, when we buy instruments, they come calibrated. And if they're expensive instruments, a lot of the stuff that we have for children experiments are just not important enough for anyone to be bothered about calibration. Like those horrible thermometers with the red Ribena in them and stuff like that. So If it's something high quality and useful, it would come with some sort of indication of how it's been calibrated and perhaps a certificate which says it's been set against a standard length or a standard mass or a standard something, so that we know that it's definitely set against the British national standards, which are linked to international standards. So you buy a device with a calibration certificate. Now, just to go to an example for you, when I did laser experiments with Varanj Bahara, he's the famous student who's we used a long steel ruler that we got in DT, and we looked it up, and it was a Japanese manufactured one, and it was calibrated, which to say that it was accurate to plus or minus half a millimeter over the entire 1 meter length of the ruler. So you could measure 99 centimeters and be confident that those 99 centimeters would be accurate to the international standard for length to plus or minus half a millimeter. So how did we use it? Well, here's my diagram then. So say I've got a chair leg, and I've got, it's off a table tennis table because they're all 760 millimeters. So if I measure it against my standard meter rule, and I've got, this black line is my chair leg, and I measure it at 760 millimeters. I've now got two uncertainties here. I've got calibration uncertainty of plus or minus half a millimeter. And you might think, well, I should add this to my scale reading uncertainty. And I probably should, but we generally don't just add them in a straightforward way. So you might think, oh, they're just going to add up, and then I'm just going to round it. And then, well, this leads to kind of exaggerating the uncertainty. Okay? But basically,